So very important. Why is my voice audible to everyone? Just check
Yes,
once.
sir.
Right, fine. 436 will you
Yes,
just
sir.
check once? Right, good, good.
సార్ ఇప్పుడు వస్తుంది సార్ వాయిస్.
Okay, no, fine, good. So all of you keep the main heading as electrical machines. That is your module number 3. Under that, DC machines. Under that, DC generators. Right. These are the topics today we want to discuss. That is the introduction about the DC machines and the principle of operation of the machine and the constructional details of the DC generator and the working of DC generator and the different types, nothing but the classification, followed by the application of the machine. See, coming to the introduction for that DC machine, always remember the device which converts mechanical energy into electrical energy is called the generator. Or you can simply make it as the machine which converts mechanical energy into electrical energy is called as generator. If we convert in a reverse manner, that is electrical to mechanical, that we can call it as a DC motor. If the supply is DC, then it will be mentioned as a DC. If the supply is AC, we are coming out of that output of the machine, then it will be called as AC machine. Right? So in the DC machine, see the generator which converts the mechanical energy into DC form of electrical energy. That is DC form of energy is the output. That kind of machine we are calling as DC generator. That is the machine which converts mechanical energy into electrical energy. That electrical energy in the form of DC, then that machine we are calling as DC generator. If the generator which converts the same mechanical energy into electrical energy in AC form of output. So that kind of machine we are calling as AC generator. In our syllabus, we are having DC generator. Understood now? So either DC generator or DC motor. Motor in the sense it is a reverse operation, nothing but the generator is mechanical to electrical, whereas motor in the sense it should be reverse, electrical to mechanical. If it is mechanical to electrical, we are calling that as generator. If it is electrical to mechanical, we are calling as motor. If the output of generator is in the form of DC electrical energy, we are calling as DC generator, right? Similarly, the supply which is provided input for this motor as an DC electrical supply, that will be called as DC motor. If you provide AC supply as an input for the motor, then it will be called as AC motor. If the output of generator is in the form of AC, then that kind of machine is called AC generator. Understood, ma? If in the case of generator, we are visualizing the output of electrical energy based on that formation, that is either DC or AC, we are calling that as a DC generator or AC generator. But in the case of motor, we are seeing the input side where the supply is DC or AC. If it is a DC, we are calling as a DC motor. If it is AC, we are calling as AC motor. Both these generators and the motors will work on the principle of Faraday's law of electromagnetic induction, whether it is AC or DC. Understood up to this?
Yes, sir.
Very, very importantly, the fundamental classes most important. See now,
Sir, your voice is fluctuating, sir.
okay. See that how the principle of operation, that is the basic principle of operation which is presented behind this DC machine. So that was the first initiated by Mr. Michael Faraday. See that in 1831, where Michael Faraday, who is an English physicist, gave one of that what we are dealing as Faraday's law of electromagnetic induction, which is giving very most and very very important law of electromagnetic induction, where you are also giving highest priority in your physics subject. Since the entire electrical should be background is based on this Faraday's law of electromagnetic induction. That is all the electrical machines are working behind this law of electromagnetic
Sir, your voice is
induction.
not clear, sir.
One second. Now check, is it audible? Was it clear, Mana? Still is there any disturbances?
Yes, sir. Some disturbance is there, sir.
Still, still it's not
Yes,
audible.
sir.
Right. No, see.
Voice is faded for some disturbance.
Yeah, okay, okay. So the slide is visible, right? Slide is visible?
Yes, sir.
Okay, okay, right. So what does it indicates? What he stated, the Faraday's law of electromagnetic induction. See, check in this figure where I think somewhere noise 412, right? Now see what that indicates, that Faraday's law of electromagnetic induction. What is this law states to us? To always remember and note it down, if possible note it down. According to the Faraday's laws of electromagnetic induction, whenever a conductor, whenever a conductor which is placed in a varying magnetic field, understood, no? Whenever a conductor is placed in a varying magnetic field, this is your field. The dotted lines indicates the lines of flux, nothing but your field. The coil is nothing but your conductor. Okay, so whenever this coil or conductor is placed in magnetic field, that is a varying magnetic field, right? So what is it going to happen? An EMF is gets induced in the conductor. EMF is gets induced in the conductor. If the circuit is getting closed, then the current will be going to pass through the circuit due to this induced EMF. What does it states? The Faraday's law of electromagnetic induction. Very important. I hope you already studied this Faraday's laws in your intermediate also. But once you have to revise. See, this is the varying magnetic field. Now what we kept? We kept one conductor in this varying magnetic field. This coil or conductor cuts the flux lines. So whenever the coil cuts the varying magnetic field, then it will be induces the EMF. So if the circuit is getting closed by connecting any load, then this induced EMF, nothing but capital E, which will induces or initiates the current which can passes through the circuit. So induced EMF is nothing but your voltage. So whenever the voltage is applicable, if you connect any load across the voltage source, then automatically the amount of current is passing through the load. If circuit is not closed, then there is no amount of current. So this I will be purely depending on closing of the circuit. Understood now the Faraday law of electromagnetic induction? So shall we write like this? According to this Faraday's law of electromagnetic induction, whenever a conductor is placed in a varying magnetic field, an EMF gets induced in the conductor. All of you note it down. Once again,
Sir,
I'm stressing.
roll number 412 is in waiting room, sir.
Allowed. All of you note it down. According to Faraday's law of electromagnetic induction, comma, whenever a conductor is placed, whenever a conductor is placed in a varying magnetic field, whenever a conductor is placed in a varying magnetic field, an EMF gets induced, an EMF gets induced. EMF is nothing but electromotive force. EMF gets induced in the conductor. EMF gets induced in the conductor system. So how much magnitude the presented induced EMF, that we can calculate by using the EMF equation of DC generator, that we can see later. Right? How much induced EMF, the magnitude value, in order to calculate, we need to derive a simple equation that is called as EMF equation of DC generator, that we can see after construction of DC generator and working of DC generator. We can learn the EMF equation of DC generator. Then shall we move on to construction details? See, in construction details, we are having stator and rotor. These are the major two parts we need to learn. So the first one is stator, the second one is rotor. Always remember the stator is a stationary part. The stator is a stationary part, whereas rotor is rotating part in DC generator. The stator is a stationary part and the rotor is rotating part. Now always remember the DC generator we can also use it as DC motor without any constructional changes, right? Why? Because the DC generator are a DC motor. So both we can broadly treat it as a DC machine simply. So the basic constructional details are valid for the construction of DC generator and motor. Both the constructional details will remain the same. So that's the reason we are calling this as a construction of a DC machine. Whether it is falls under DC generator or it will falls under DC motor, the construction will be remains the same. Understood now? So if you learn the construction of a DC generator, by default you also learned the construction details of DC motor. The only working principle is going to differ from one machine to another machine, that is generator to motor. Construction is remains same. So how many parts we are having? Two parts, right? So the first one is a stator and the second one is a rotor. These are the main parts of the DC machine. But if we go for internal view of the DC machine, there is a different parts where we can analyze individually. Right. So here what we learned, the stator, which is a stationary part, in order to provide the magnetic fields where the coil can spin, nothing but where the coil is going to rotate, the coil should be going to place in a magnetic field. So that support the provision should be done by the stator part. That means the stator will be includes that magnets with opposite polarity facing each other. That is a north and south. Opposite polarities facing each other. Two magnets. The rotor, which is nothing but a rotating part or moving part of a DC generator. It simply rotates due to presence of the wires and the magnetic field of the machine, which can be arranged so that whenever there is a rotation, there is a torque is going to develop about the rotor axis. That is in the case of a DC motor. Now see, this is the most important diagram where you have to draw in your examination. This is the mandatory diagram you have to draw. See here the outer part. First you have to identify the name of the components which are presented in the construction of DC machine. See this first one, that is yoke. The yoke is nothing but the mechanical support which is provided for these poles. See, these are the poles. So one by one we can go. First you have to just see the diagram. Yoke, pole, these wires we are calling those as a field winding, and the internal cylindrical structure whatever you are visualizing is called the armature. The slots which contains a dotted symbol that we can calling as a conductors. See here, these are the armature conductors, right? And one more, there is a circular shape is available that we can calling as a commutator. And above that commutator, there is a square shaped black boxes are available. These we can calling as a brushes. And obviously the terminal box where which can carry the input wires and output wires. See, these are the two input wires and these are two output wires. Right? Understood? The components which are presented in a DC machine. This internal cylindrical surface, that shape we are calling as the armature. Very important. That is nothing but your rotor part, the rotating part where the conductors are placed in the slots. Those conductors which are placed in armature slots, which are called as armature conductors. And internally, that will be going to connected with the commutator. So this commutator again, we are having some slots which are separated by some thin mica, right? And above that, we are having some brushes. Brushes, the use for brushes is in order to collect the current or the voltage which is induced in it. And that will be getting communicated to the output through the terminal box connection in this way. We will go in detail part by part. So the first one is a yoke. So what is the purpose of yoke? Which is a outer frame, which is a outer frame where it can provide the protection to the rotating and the other parts inside the machine from different factors which are presented in atmosphere. That is a moisture content, dust, and various factors and gaseous components which are going to interact to provide the chemical reactions. So such incidents are we are going to avoid in order to maintain the lifetime of the machine. So for that reason, the yoke which plays a very vital role to provide the protection to all the rotating parts and the stationary parts which are presented inside the machine. So this outer periphery of that DC machine we are calling as the yoke. So generally it should be made by the cast iron or the iron body that provides the path for the flux. So the path for the flux it should be need to provide in the sense it should contains the low reluctance, where reluctance is nothing but reluctance is to oppose the flow of flux. So that's the reason we need to provide low reluctance. So low reluctance in the sense it should be allowing the maximum amount of the flux, and it provides the mechanical support. Of course, we discussed it till now for the poles, and the materials what we are using for yoke is cast iron, what I mentioned. Cast iron, and somewhere we can go for silicon steel and rolled steel, but the majority of the DC machines are using this cast iron material for the manufacturing of your yoke of DC machine. And followed by, so this yoke what we are learned, it will provide the protection, the first priority, and low reluctance. Rather than low reluctance, here I will mention the material what we are using. It should be having very low reluctance on, and the material is cast iron. Now see the second part, that is force.
Your voice is not coming.
Hello, was it audible?
No, it is.
Okay, fine. So up to yoke, it should be clear to everyone. Clear
Yes,
more,
yes.
all of you up to
Yes.
yoke. Right. Next, poles. So poles to produce the magnetic flux, right? The pole in the sense the field windings are getting wounded on the surface of a pole. See, this is what you see in the figure. The pole, it will be looks like the shape of your shoe. So why this kind of shape? This is the pole complete we are calling as the entire symbol. So on this pole we are having the windings. These windings are called as the field windings, or we can also call as excitation windings. That means where the input supply coming from the terminal box is connected here. Okay, this is going for another pole, and one line should be for this pole. So this winding which is coming from the terminal box to this pole, which can be mounted on this pole surface, we are calling as the field windings. And the shape why it is coming like a shoe, so this we can also call as pole shoe. This is for the spreading of the flux. This is for spreading of the flux from one pole to another pole, like this, spreading of the flux. Like this we are having 4 poles. So the spreading of the flux from one to another, right? In between that, in center we are having the armature. Now see, the materials which are used for these poles are cast iron once again, or cast steel. The majority we can use as the cast iron. What we are doing on these poles, field windings are getting wounded on the surface of a pole. Right. So what is the material? Once again, it is cast iron or cast steel. And here we are mounted with field windings. Then what is the purpose of this field winding? See that what I mentioned here, in this pole, the field winding is coming from the terminal box, right? And another field terminal. These are the input two terminals. This is the one, and this is the second. And these 3 and 4 are the output coils which are going out. That is to communicate the DC electrical energy through the brushes to terminal box. This is the input supply, right? And the field windings which are made by the material copper. Here I mentioned here, right? See, the metal or the material we are using for this field conductor is copper material. You may have one doubt, sir, copper and the aluminum, both we can use. So why only we are using copper rather than aluminum? Both are having good conducting properties, right? But why we are using copper in the sense due to the cost point of view and also the flexibility. Copper we can easily turn or the twist according to the shape of the winding, what we can call as a winding. So how we wanted to wound on the particular pole, we can do that with the flexibility of a copper wire. Whereas aluminum, that type and that kind of flexibility is very quite less compared to copper, and also the cost point of view also. So this field winding we are also calling as excitation winding, where excitation is also called as input. Simply the input, or we can also call it as excitation. So this excitation winding we are also calling as a field winding. So what is the purpose of this field winding? The current which is carrying or passed through the field winding in a specific direction in order to magnetize the pole, in order to produce the magnetic field, varying magnetic field, the flux lines, right? Understood? So the field winding which is carrying some current which can magnetize the pole, and therefore the flux is going to develop, and the armature conductors cuts the flux. Therefore, the EMF is induced. Right? Understood now?
Yes, sir.
Yes,
Uh, Log out and re-log in, or else you can check with your audio cables, earphones. Right. So the field windings which can be made by copper material, right? Copper material, and the purpose of field winding is to carry the currents in order to magnetize the particular pole, right? And purpose of armature and the armature conductors. Armature conductors, wherever the word conductor, that will be made by copper. Remember by default. Okay, whenever there is a word copper, you must remember that should be made by copper material. Now see the armature. So in this armature, it should be very, very important. We have to maintain the low reluctance path, nothing but where we can allow the maximum amount of the flux, right? Therefore, to the flux produced by field winding. So how much amount of the field winding is magnetizing the pole? So that amount of a flux is going to develop, that will be passing through these armature conductors where we are placed in the slots of it. See now, this is your theoretical textbook diagram, the first figure. Here you are having some slots and the laminated ways, and see here the air holes which are provided for cooling purpose. Okay, the air holes which are provided for cooling purposes, and these are the slots, right? In between these two laminated wounds we are having some slots. So these slots are filled by some conductors. So this is the conductor. So see in real time diagram, in between one slot to another slot, there is a copper wire which is wounded, right? So this copper wire, what we are calling as armature conductors. So these armature conductors which are placed in slots which are parallel to the shaft. This is your shaft. This straight line is your shaft. So which are parallel to the shaft axis. So this core should be again made by the material cast iron. So this is the core where which can maintained by made by the cast iron or cast steel material. In between the slots, whatever we are provided, the conductors, that should be made by copper material. So where we stopped here, armature. So armature is made by which kind of material? Cast iron. or cast steel. Next, what is the purpose of armature? Where which can provide the low reluctance path, nothing but how much amount of the magnetization of this pole happened due to the field windings, right? Such amount of flux is going to spread over the armature conductors. So these armature conductors, which are placed in the slots of armature, can cut the flux and a particular EMF is gets induced. EMF induced in the sense of the circuit is closed by this terminal box, then the current is going to pass through the terminals which are connected to that terminal box. That is from brushes. Now see, this is your commutator. This is circle. So what is the purpose of commutator? Commutator is nothing but a rectification process. So where the physical connection to the armature winding is made through this commutator and brush arrangement. These are the brushes and this is your commutator. Just to see how it should be in real time. Right, see the textbook diagram and the real time. This commutator where which can converts the alternating EMF generated internally into a DC voltage. That what I mentioned as a rectification process. Rectification. What does a rectifier property? The rectifier is which can converts AC into DC. Right?
Fire कैसे होता रहता है ना?
So here also we are converting that as AC into DC format. Right? The commutator which converts the alternating EMF generated internally in DC voltage. That is from AC generation to DC. The output is always DC. That's the reason we are calling this as a DC generator. So what it's going to do by using the brushes is which can collect the current from the armature conductor and passes it to the external load. Understood now? How much amount of current which is passing that should be getting collected in armature conductors, right? And that should be connected to your terminal box connection. So
Sir, your voice is again fluctuating.
quick response.
Sir, your voice is again fluctuating. Sir. Can't hear.
For remaining, I'm asking 401, 402. 404.
Yes, sir.
Is my voice audible?
Yes, sir.
Yes, sir.
Is there anyone having that issue now where my voice is not clear or fluctuating, having disturbances?
Yes, sir. Sometimes in the
It's
middle,
not
sir.
clear, sir.
Yeah,
Yes,
okay.
sir.
Right.
Yes, sir.
Right. Now is it clear? Just reconnected my audio. Is it audible now?
Yes, sir.
Right. So see where we stop that commutator and the brushes. So in that everything where we need to understand the complete operation of the DC generator based on this instructional parts of DC machine. So what is the commutator? Just to have to revise this commutator where which will consist of the copper segments which are insulated from each other. So these number of segments is always equal to the number of armature coils. But what we say, just we have to bring it into the commutator. So here how the segments, these copper segments we are having, which are getting connected to the armature coil and the commutator, which is further connected to the shaft. This is the shaft. So brushes are usually made from carbon or the graphite material. So the purpose of brushes was that in order to collect the current. So the purpose of the brushes is to collect the current which are made by the material carbon. Here the commutator is which contains copper segments.
Sir, your voice not audible, sir.
No, why still it's facing audio issues? 59.
Sir,
Still not audible?
yes, sir. Now it is audible. Now.
Yeah, fine. Right. So here copper segments, where we are having the two copper segments, the set of copper segments which are insulated from each other. This one, what I'm talking is, see on the pointer, the commutator, the internal circle shape. So this shape should be having a segments. So these segments which can be separated by a mica sheet, that is a mica material where the thick small line is the mica material which can separate the set of copper segments. Set of copper segments. How many segments we need to keep? That should be depend on the number of armature coils. Okay. So here there is depends on armature coils or conductors. Understood, all of you? The constructional details of a DC generator or DC motor, simply what we are calling as a DC machine. Clear the constructional parts and its importance, why we are taking the part in this machine, starting from
Yes,
yoke,
sir.
to ending from terminal box.
Commuter.
Clear, right? Purpose of yoke, purpose of poles, purpose of field winding, and what are the different materials we are using to manufacture those materials, purpose of armature conductors, purpose of commutator, purpose of brushes, and the purpose of the terminal box. Clear, done. So shall we go for how it should be going to work? That is nothing but how it is going to generate the DC energy, electrical energy, right, as the output of the machine. Shall we look into that working operation of this DC generator?
Yes, sir.
Yes. See the working of the DC generator. See, these two are the poles that what we see in that constructional part, that is a north pole and south pole. Okay, and this is the coil. Right? This is the coil. Coil is the armature conductor. So this coil is connected to what? The commutator. So this is your commutator. These two square shaped boxes are called the brushes. The brushes which are fixed on the rotating part of this commutator. Commutator will rotate now, but brushes won't rotate. Those are fixed on the surface of the commutator. Remember, brushes won't rotate. Only the commutator and the coil will rotate. And of course, the flux, that is the field lines, are presented in between one pole to another pole. That is from north pole to south pole, the field lines are presented, the magnetic field lines. this wire, that what we are calling as a conductor, that is made by a copper material. Done. Now, how we are going to generate the DC output? See, in this description, what it consists of a single loop of wire that rotates in a magnetic field. This is a magnetic field which is varying according to the development of the flux. That development of the flux is further depends on the field winding excitation. So how much field winding is magnetizes the pole. According to that, the field lines will be going to presented in between one pole to another pole, right? So here I am taking a conductor which is placed in between this varying magnetic field and this conductive metal ring, what we are calling as commutator, that is this one, which is getting connected where it is a rotating part and the direction of current from the rotor to external circuit. This is our circuit, external circuit. Here where we can connect some load, that is a resistance or inductance, what it depends on the situation, we can connect a load. So here as the wire loop, which can wire loop in the sense this conductor, which can rotates in magnetic field. That is lines which are indicating from north pole to south pole. So this wire loop rotates in a magnetic field. The split commutator ring also rotates. So the wire is getting connected to this commutator. What I mentioned, commutator is a rotating device, right? So whenever this wire is getting rotating in this magnetic field, corresponding the commutator which is connected to this wire is also going to rotate according to that axis, right? So each half of a split ring rubs against the fixed contacts, that what we are calling as a brushes while rotating, which are placed against the rotor of a generator or motor, whatever we are calling that machine, in order to make an electrical connection between the fixed part and the rotating part. So the brushes connect the rotating wire to the external circuit in the sense through the terminal box. This is the external circuit. Now see, let us take, there are four positions. There are four positions here. A, B, C, D. Like that. Or understanding the operation, here I am taking a 4 points. Very important. Just to focus for 5 minutes, you will understood very clear the operation, how it is going to generate the DC output. By taking these 4 points, very importantly, by taking these 4 points such as A, B, C, D, these are the flux lines which are coming from North Pole to South Pole. The same diagram precisely I given here. Okay, this is not a new diagram. Just by indicating the points A, B, C, D for our references. See that at position A, right? At position A, the loop is effectively moving parallel with the field, right? Parallel with the field in the sense the lines, see, the both are in same direction, right? Understood? The blue color indicates the field lines, that is the flux lines, and the red color what I drawn, that indicates the coil direction. Okay, now both are in same direction or not? See in this figure 1, both are in same direction, the coil and the field lines. Right?
Yes, sir.
Understood. So both are in same direction in the sense the angle maintained is 0 or 180. So 0 or 180, sin 0 or 180 is 0. The magnetic flux lines is 0 at position A. Right? Now, now we are shifting from A to B. See the direction, the pink color. Now we are shifting from A to B. So while we are shifting in the sense, what is going to happen? We are cutting the flux lines step by step, increasing, 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 and reaches exactly the perpendicular here. At B, we are achieving the perpendicular direction. So perpendicular direction in the sense it should be the maximum amount, right? The maximum number of lines we are cutting, that is moving perpendicular to the magnetic field where at position B. So as the loop rotates from position B to C further, it should be again cutting, cutting, cutting. That means we are decreasing, 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 and then it will be 0 again in parallel path. Understood? So the first area, that is at 0, right? Later from A to B, which is increasing, later which is a decreasing. This is A, B, that is maximum increases up to the perpendicular, and from B to C, it is a decreasing mode and that reaches 0. And if you shift, that is minimum at a C point now. See in this description. And then after C to D, again what is going to happen? Cutting, 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 increasing, and now it is in perpendicular direction. But in downward, whatever the direction, whether upward or downward, it is perpendicular to the field lines. That means again increasing up to the point D, and from D to A, cutting, 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 that is reducing to 0. That is in parallel path. That means D to E flux cutting EMF is reducing, reducing, and reaches again 0 point. So like this, it will be continuous. Now are you able to visualize the unidirectional waveform with some magnitude? Understood now? How we have generated the waveform?
Yes, sir.
See that whatever I explained till now, the same here. From A to B, the same direction. This portion is developed from B to C. Portion developed C to D, increment, and D to A, further decrement. The same diagram what we drawn here, A, B, C, D, A. Clear? So in examination, you need to draw these 4 diagrams along with the first diagram, this one, under the heading of working of DC generator. Very simple. You can elaborate your own words. Okay. First, you have to study 1 or 2 times, then it will be easily to understand how the output is getting generated. So this is your output waveform of DC generator. For the first rotation, second rotation, and the third rotation. The formula what induced EMF is equals to the B is nothing but the flux density which can be produced as per the perpendicular to the motion. That is a maximum amount of flux will be presented. And L is nothing but your length of the conductor. V is the velocity, right? Velocity of the conductor. See here, V is the velocity of the conductor. Now, is it understood? The working principle, all of you? The construction and working. Very, very important. Question in examination. Understood all of you? The construction details, and for construction we need to draw this diagram. This is the only diagram required. The remaining is as per your wish. Either you have to draw or no need to.
Sir, again voice got fluctuating. And
Yeah,
it is low, sir, very low.
Now it should be clear, I think. So for construction,
Yes,
this
sir.
is, yeah, for construction, this is the one diagram you need to draw. The rest of the diagrams is your wish based on your capability, but marks should be completely given for this diagram. Diagrams should be very, very legible. You have to draw, right? And the remaining diagrams no need to draw. If you draw, that should be well and good. Here why I am doing all this in the sense in order to understood from theoretical to practical. This is your theoretical textbook diagrams. This is what we are having in our laboratory. The both I am going to visualize to you to understand better how it should be in real time, how in the textbook. So similarly, the commutator, this is your practical commutator, this is your textbook diagram, and the working principle followed by the classification. This is not required, no, but you have to just remember how we can classify. That is, what are the types of generators we are having. That is a separately excited DC generators, self-excited DC generators. Separately excited in the sense it should be having its own machine, that is own, or what we can call independent, right? Is having its independent supply in order to excite the field windings. So in order to excite the field windings, we must have the own independent source or supply. Here in self-excited generator, it should be getting excitation by the residual magnetism. The residual magnetism in the sense the magnetic field which is stored inside, right? That should be going to a small amount of magnetic field which is stored, that should be going to initiate the field windings in order to magnetize the pole, in order to provide the flux lines, nothing but the field lines in between North Pole and South Pole, in order to cut the armature conductors where the EMF is getting induced as per our Faraday's law of electromagnetic induction. So generally what we are having is self-exited generators in our regular applications. So under this self-exited generators, we are subclassified into the shunt generator, series generator, and the compound generator. This compound generators further classified into two kinds, that is a cumulative type and the differential type. So this cumulative further subclassified into long shunt and short shunt cumulative, and the differential further classified into long shunt and short shunt differential generators. So this long shunt and short shunt should be depending on the nature of the field windings we are keeping. The winding arrangements going to modify, the name itself going to modify. If the field winding is in series combination, that what we are calling as a series. If it is in shunt, that is a parallel, that is a shunt generator. Both the series and shunt are getting included, that what we are calling as a compound generator. So these are the different types of generators what we are having in practical cases, and where we are going to use these generators in our real time, that is application point of view is that where the general for our functions occasions we are using the generators which are majorly used for the lighting of loads and the charging of the batteries, the inverters, right? That is a shunt generator, and the arc lamps, the constant current generators, boosters. For these all we can go for the series generator. Whereas for electroplating, electro refining, that is in industries where we can go for the separately excited, and the domestic lighting and the transmission lines, we can go for the cumulative compound, and electric arc welding, that is a pure mechanical portion where we can use the differential compound generators. Right, understood now the various applications of the different kinds of generators where we are going to use.
Yes, sir.
So I hope everyone understood the construction. Now, what is it meant by DC looping and the DC generator? And what is the purpose of DC generator? The construction details, the principle of operation, that is Faraday law of electromagnetic induction, and working of the DC generator, and finally the types of DC generators and the applications of DC generators. Where we must have to learn the EMF equation. That is very, very important. Just more time for 1 minute. Keep the subheading EMF equation of DC generator. So what we have learned from Faraday's laws of electromagnetic induction, we know that E is directly proportional to d phi by dt. That is from Faraday's law. Right. So here phi is nothing but flux per pole. Here you need to write now. Phi is flux per pole. The units are Webers. P is number of poles. Z is total number of conductors. Total number of armature conductors. Just to focus for 5 minutes more, we can conclude the session. And how much speed it will going to rotate, that is capital N, which is the speed of armature in RPM. These are the units RPM. And how many parallel paths we are provided, that is represented by capital A, that is the number of parallel paths, and the P is of course the number of poles. So from this Faraday law of electromagnetic induction, this is your average induced EMF per conductor. Now, if the flux cut per conductor in one revolution, if we want the flux cut per conductor in one revolution. One revolution in the sense it should be d phi is equals to number of poles and flux. How much amount of flux that should be touch that pole? That is a d phi is equals to the flux cut per conductor. Here also we can mention flux cut per conductor in one revolution. That is d phi is equal to p into phi Webers. Units are Webers. That is the rate of change of flux. Simply we can call it as. Now the time taken for one revolution, how we can take the time taken for one revolution. See here, I taken the units of the speed in RPM. RPM in the sense revolutions per minute, right? Revolutions per minute. So if we want in terms of seconds, that is dt. Here it is. d5 we written, now dt. So if it is per second, that should be 1 minute is 60 seconds. So therefore 60 by n seconds, where n is nothing but speed, RPM. Now substituting both in average in EMF used, that is average EMF used in DC generator is equals to d5 by dt, where d5 is nothing but p into 5 and dt is nothing but 60 by n. That is p5 n by 60. Now the EMF, note down the EMF, nothing but total EMF. This is average. The total EMF generated between terminals, that is EG. That is EG, that is total EMF generated between the terminals, that is generated EMF. EG is equal to your average EMF generated per conductor, that is this one, E average, this one multiplied with the number of conductors in each parallel path. So 5p5n by 60 into, that is average induced EMF into number of conductors in each parallel path, nothing but Z by A, where A is parallel paths, Z is number of conductors. See here, Z is total number of conductors and A is number of parallel paths. So the number of conductors, Z is number of conductors in parallel paths, that is Z by A. So therefore, shall I conclude as EG is equals to 5ZNP by 60A. This is the EMF equation of DC generator, very important for problems. So how we can calculate the EMF of DC generator? By using the formula of 5ZNP by 60A. So EG is equals to 5ZNP by 60A, where 5 is the flux per pole, Z is total number of conductors, N is speed, that is RPM, speed of armature, and P is number of poles, and capital A is number of parallel paths. So up to this, you need to remember perfectly as per your syllabus. If a little bit of stress they wanted to make in your question paper, they may mention as lap winding and wave winding. That is the how the armature winding we can keep. If it is a lap winding, remember A equal to P. That is in numerator P and A will be getting cancelled. The EMF equation is 5 by 60. If it is a wave winding, the value of A is always 2. These are important for your multiple choice questions. For lap winding, parallel paths is equal to number of poles. For wave winding, number of parallel paths should be restricted to 2 only. Only 2, number 2. Very important now. Note down EMF equation of DC generators. Once noted, inform me so that we can wind up the session. Now, Vedant, meanwhile, you can take the screenshot of attendance, today's attendance, and post to my group.
Sir, I already sent it, sir.